Watch this whole simulated patch of space. 10,000 faint stars move through an idealized gravity run. The amber ring marks one star we will follow, and we will keep watching it as we change scale. Keep watching that same amber star as the view closes in. It is not a lone point. In our model, a planet orbits it, a moon follows that planet, and a broad belt of smaller bodies fills the system. There is no cut to a different example. We are only changing the scale at which we look, while the same objects keep moving under the same force law. The belt now contains 10,000 idealized asteroids. For this opening demonstration, each small body follows an orbit under the fixed star's gravity. The bodies are moving, but we are not yet claiming that they perturb one another. This run makes the scale visible before we turn on every mutual interaction. Now let the bodies pull on one another as well. The cyan target feels a contribution from every other body, not just from the star. That is the computational problem for this episode. The physics stays familiar, but the number of force visits becomes enormous. This collisionless particle sandbox represents a flat slice through a gravitating cloud. 10,000 bodies pull on one another, and the cyan body is our tracked probe. The force law is still ordinary Newtonian gravity. The new problem is how often the simulator must evaluate it. Which aggregation policy should replace the exact sum? Should every outlined cluster act as one mass? Should every cell open until every body is visited? Or should only distant compact cells act as one mass? Commit to one complete policy before we trace the force.
I would let every outline cluster act as one mass because each cluster keeps the same total mass.
For one target, the exact sum visits the other 9,999 bodies. Across all targets, that is 99,990,000 directed contributions. A symmetric direct implementation can reuse each action-reaction pair, but 10,000 bodies still create 49,995,000 unordered pairs. Mass alone is not enough. A nearby wide cluster can pull in a noticeably different direction than one point at its center of mass. We need a spatial map that preserves nearby detail and compresses only the geometry that looks small from the current target. The direct sum is exact, but it gives the probe no way to spend less work on distant structure. A quadtree supplies that missing spatial map. It begins with one square containing the planar world. If an occupied cell needs more detail, split it into 4 children and repeat. Dense regions grow deeper branches, while empty or sparse regions stop early. Each leaf knows its bodies. Each parent adds the masses of its children and computes their shared center of mass. This summary travels upward until the root knows the mass and center of the entire cloud. The stored center of mass now has a job. From a distant probe, this compact cell may replace 8 separate force contributions with one aggregate contribution. The exact arrows remain our reference. The amber arrow is cheaper because the tree walk accepted 1 cell instead of visiting 8 leaves. The picture is 2-dimensional, so every split creates 4 children. A 3-dimensional gravity code normally uses an octree with 8 children. The organizing idea is the same. Spend spatial detail where the target can resolve it. The tree has summarized every occupied cell, but the target still needs a rule for deciding whether a summary is detailed enough. Our displayed rule compares a cell width, called S, with the distance from the target to that cell's center of mass, called D. Accept the aggregate only when S divided by D is less than the chosen threshold, theta. For the distant probe, the ratio is small, so the tree walk accepts the whole violet cell. When the probe moves closer, the same cell looks wider. The ratio grows past the threshold, and the walk opens its children. Now move the probe inside the cluster. Should the containing cell remain aggregated, should only its nearest child open, or should every containing branch open until the probe is excluded from the accepted aggregates? Choose one complete rule.
Every containing branch should open, because an aggregate that includes the probe would give it a self-interaction.
Exactly, every cell containing the target must open. Nearby sibling cells may also open because their size-to-distance ratios are too large. Far siblings can still collapse. One tree therefore produces a different set of accepted cells for every target body. A smaller theta demands more opening and usually more accuracy. A larger theta accepts more cells and usually does less work. The ratio is an accuracy control, not a theorem promising one fixed global error. The particle distribution and the chosen error metric still matter. The opening rule saves work by accepting an approximation, so neither the picture nor the rule alone can tell us whether the trade is acceptable. We give both methods the same seeded positions and masses in two test clouds. One method uses the direct force sum, and the other uses the tree. We compare force call counts instead of wall time. The two implementations use different languages and libraries, so a wall time race would not be fair. At 1,024 bodies, theta equal to 0.3 uses about 18% of direct work for the uniform cloud and 20% for the clustered cloud. At theta equal to 1, those fractions fall to about 3% and 5%. The saved work has a price. Global relative force error rises from about 0.05% at theta 0.3 to 1.33% for the uniform cloud and 1.74% for the clustered cloud at theta 1. Suppose the displayed requirement is global relative force error below 1% in both clouds. Which is the largest tested theta that passes? 0.5, 0.8, or 1.0? Commit before the threshold line appears.
I choose theta equal to 0.8 because 1.0 already exceeds the 1% line.
The short trajectory check keeps the initial state, softened force law, and velocity Verlet integrator fixed. For the clustered cloud, final position error grows from 0.11% of the system radius at theta 0.3 to 2.03% at theta 1. The measured momentum drift also grows because this ordinary target-to-cell traversal is not pairwise symmetric. These curves describe one implementation, two seeded distributions, and named error measures. They do not certify every tree code. They do show the decision we need. Select theta against a measured accuracy budget, then repeat the test on inputs resembling the intended simulation. Tree approximation and time integration are separate choices. Our trajectory test used the same velocity Verlet update on both sides and changed only the force evaluator. That isolates tree error from time step error instead of mixing two explanations. The trajectory test also used Plummer softening. Replacing distance cubed with softened distance cubed prevents an unbounded force at zero separation, but it modifies gravity inside the softening scale. The softening length is part of the physical model, not a secret repair switch. A symmetric direct pair gives equal and opposite forces in the same evaluation. An ordinary tree walk computes target-to-cell forces separately, so exact cancellation is not automatic. Symmetric hierarchical algorithms exist, but this implementation must measure momentum drift rather than assume it away. A responsible workflow keeps a smaller direct reference. It records force calls and several error measures. It checks trajectories and invariants. It publishes the opening threshold, the softening length, and the time step. It also records the particle distribution, the random seed, and the source revision. Approximation becomes trustworthy through a repeatable contract. Barnes-Hut can make a huge calculation cheaper, but it cannot give a measuring instrument more precision. Imagine that our instrument reports one body's horizontal position only to within 5 parts in 100,000. The green start and the magenta start differ by 1 part in 100,000. Both starts fit the same reported measurement, so the instrument cannot tell us the exact positions and velocities that the system actually has. Both possible states follow the same Newtonian gravity. Should one computed path remain a useful representative for both possible futures, or can a close encounter pull the two possible futures apart? Choose one complete prediction before the calculations run.
I predict that one path will remain a useful representative because the two allowed starts are much too close for our instrument to distinguish.
We begin after both states have already passed several close encounters. At this scale, their configurations are still visually identical. Each panel uses the same world scale, the same three masses, and the same gravitational equations. Now let both calculations pass through another close encounter. Their paths first separate slightly. The next gravitational interactions act on those new separations. Soon the two allowed futures no longer describe the same configuration. We also repeated both calculations with tighter numerical settings. Each tighter calculation stays close to its corresponding original calculation through the onset of the visible separation. That numerical disagreement is much smaller than the separation between the two allowed physical states. This confirms that a loose numerical step did not create the split. However, a tighter calculation still cannot tell us which starting state nature chose. Nothing random was added. Each exact starting state still has one exact future. The limit comes from what we know, because one measurement corresponds to several possible states. A physics engine can make a trustworthy short-range forecast, but it must stop treating one path as certain after those possibilities have separated. More computing power solves the scale problem. It does not erase measurement uncertainty. The next and final episode turns from long-range prediction to one practical task. The simulation will include gravity and thrust. It will track rotation. Springs and damping will shape the legs, while contact and friction will decide whether the lander settles on a tumbling asteroid.